Okay, so you can see all of this over here, the windows over here and the PowerPoint here.
Looking good.
Okay. All
Cool.
right.
So our final project was developing OpenGesture, customizable computer control by recognizing hand numerical gestures.
All right. So first of all, let's start off with the introduction. Okay, so for some technical background, with more and more powerful devices and algorithms, computer vision is more popular than it has ever been. We see it in our computers and cameras all the time. It's the reason for Snapchat filters, object detections, and self-driving cars, and artificial intelligence. Okay, so we wanted to expand our knowledge about camera vision through the creation of this project. We saw that there was a huge opportunity to control computer devices with non-conventional controls, that is, cameras. These devices might be televisions, computers, smart home devices, or even robots. So we decided to take up the task of building a basic input simulation program to learn the basics of computer vision. So for our project, we created a program that runs a customizable keyboard or mouse input command based on the number of fingers that you are holding up. So for this presentation, we use the following setup. So it's currently the fingers held up are on the left side and the command it runs is on the right side. So for example, like we have the number 1 over here, doesn't do anything because we didn't really bind it to anything. But then if I put up the number 2, it's going to move on to the next slide. If I put up the number 3, it's going to go to the previous slide because I binded the number 2 on my fingers to the down arrow key on my keyboard and the number 3 on my fingers to the up arrow key. And then 4 and 5 are not binded either because we didn't really need those. So as for practical applications, we are thinking that as the project currently stands, we can see it helping out people during a presentation in which the speaker could be making hand gestures to move between slides instead of relying on an expensive clicker or a second person to change the slides for them. It could also be adapted into a media player, gesturing for music to start or stop, to raise or lower the volume, skip songs, etc. And this program could also be used to assist anyone remotely, interact with the computer for any other reason that we have not listed here. And we will have some future possibilities of this application that we're going to be listing later on. So, original algorithm.
So we use an existing algorithm as a base. We essentially use an adaptation of an adaptation of an original algorithm that was intended to be really computationally fast and used in robots. So we make some optimizations to it, and we also adapt it for general computer control. So how does this algorithm work? Well, the first step with any computer vision problem is preprocessing.
Oh, okay. Had to focus the window.
So as you can see, there's this green square that you have to put your hand into. And so the first step is to extract the image from that green region of interest. And in computer vision terminology, this is usually referred to as an ROI. So we take the frame, we resize it to 700 by 700 pixels, we mirror it horizontally and convert it to grayscale. This is just to make sure that, for example, skin color doesn't affect the quality of the finger counting. We also Gaussian blur the entire frame to make sure that no rough edges just like throw off the entire image. And all of this normalization has the effect of making sure that we get similar results when different people use it in different backgrounds and different settings. So the way we actually detect the hands is really, really simple. When the program starts, we use the first 50 frames of the program to compute what's called the running average. And so we basically keep the average of each pixel in the background. And now, when we use a frame, if the pixel is sufficiently different from the average we already had in memory, then count that as part of the hand. And on the debug, this is drawn as the gray hand on the image. And as you switch to slides, you'll be able to see it. So the next step is to figure out where the center of the palm is. And so the way we do this is first compute the contour of the hand, which is basically the boundaries of the hand. And there are really, really fast ways to do this already. And the next step is to compute what's called the convex hull of the hand contour. And all this really is the convex polygon that is able to contain the hand. And why we do this is that now we can compute the extrema of the convex hull, so the topmost, bottommost, leftmost, and rightmost point of the hand. And you can see the convex hull as the blue points in the hand on the demo, on the debug. And so we just take the average of the topmost and bottommost point, and then the average of the leftmost and rightmost point, and we assume that to be the center of the palm, which is the yellow dot on the middle of his hand there. Cool, so here's the actual finger counting algorithm. First, we construct a palm circle from the center of the palm with radius, so one back slide.
Oh, next slide, sorry.
Yep. Cool, so we construct the palm radius with radius 0.8, so 80%, times the maximum distance from the center of the palm to any extreme on the convex hull. If you look at your hand, this is usually from the center of your palm to the top of your middle finger. And so we take 80% of that and then construct a circle. And so now once we have the circle, all we need to do is compute the intersections of the circle and the original thresholded image using a simple bitwise AND. And because bitwise AND is in the computer at the machine level, this is super, super fast. So the remaining binary image, which you can see in green, basically contains the arc contours for each of the fingers. But the final and important step is that we only count a green arc as a finger if and only if the contour is not the wrist, so it's not below the palm, and it also does not contain a number of points that exceeds 25% of the palm region circumference. The idea is that each finger should be pretty small and have only a really small intersection of the circle, and also to make sure that the wrist doesn't get counted. So if you'll go to the next slide, here's a picture of what the original algorithm looked like. And there, right off the bat, you can see that there are several problems with this. First, the circle goes above the pointer, and the thumb is counted as part of the wrist. And both of these problems are a result of the fact that the center of the palm is way too high. The center of the palm is like in between the pointer and middle finger when it should be like in the center of the hand. And plus, the count fluctuated wildly when we first implemented this algorithm. And that's really bad for computer control. You don't want to be like constantly moving between slides when you're trying to use it for presentation control. And so we had to do some pretty deep problem solving, and we came up with some clever solutions, and Gatlen will be explaining that next.
All right, so here's our improved algorithm. And just an FYI, what you've been seeing down right over here, and this right here is what we call the debug panel. That's what you've been seeing, the improved algorithm and not the original algorithm. So I'm gonna go ahead and move on to the next slide. Okay, so first of all, instead of using the full circle like it was being used in the original algorithm, we decided to use instead the upper segment of an ellipse. So this essentially has the effect of cutting out the wrist entirely, and then it also brings the arc down a little bit lower. So that way, instead of detecting the very edges of the fingers, it detects about the midpoints or sometimes even the base of it, which is extremely helpful for people that have smaller hands. And also it is less volatile when it comes to noise being in the image. The next thing we changed was instead of using the midpoint between the extrema of the convex hull enclosing the hand, we used the moment. So before I go into that, let me go ahead and explain what the midpoint between the extrema of the convex hull and the closing of the hand is. So essentially, if we were to think of like an entire box surrounding my hand, the midpoint would be halfway between each part of the box. But what that would do is because it would essentially bring the center all the way up toward like the fingers. Meanwhile, instead we use the moment, which is kind of like the center of gravity or the weighted average of my fingers. And that puts the center point more in the direct center of my palm. So the next thing we did is to account for no fluctuation or transition accounting. So essentially, like when I say transition accounting, I mean, imagine if I had no fingers up in there, and then I transitioned all 4 of my fingers onto there. Before there's going to be 1 finger, and then there's going to be 2 fingers, and then 3 fingers, and then 4. And that would have just ran like 3 different commands on my computer that I don't want it to run. So instead, we used the time that the fingers are consecutively held in the frame to account for the fluctuations. So in case there's some sort of error, it kind of removes that in case it's like flickering between 4 and 3. And it's also accounting for me moving my hands in. Next thing we did is we also put the gesture-based commands, which are read in from a YAML file, which is right over here. So essentially, this is what we were talking about before. Second finger is bound to down, third finger is bound to up. The first one's actually bound to Control-C, but it's whatever. So these are how we've been controlling it. 2 fingers coordinate with down, 3 fingers coordinate with up. So that's kind of specifically for our program. Next thing we had was a hackable number recognition class, which can be inherited from and altered. So if you guys wanted to take the class, you could inherit from it and change any of the functions you wanted to do. So you could change how the settings file is read in. You could change how the center of the palm is detected, how fingers are counted, how the background is removed, etc. And lastly, we included our complete own debug image screen, which I already showed you right down here.
Just to add on, for point 2, we put in a lot of effort and time making sure that almost every little task that's actually done by the program is in its own function. And so when you like inherit and override a method, it's really easy to make meaningful changes.
All right, let me go to the next one. I already demoed it for you. So let me go to the next one.
So there are a couple of future changes that we'd like to implement. The original circle algorithm allowed you to rotate your hand and still be able to detect fingers. However, this method is really efficient when your hand is still, but doesn't work when your hand is rotated. So we have a couple of ideas to fix this. First, we might take the topmost extrema, which would be like the middle finger essentially, and somehow use like that vector to rotate the ellipse. We'd also like to have real-time hand tracking, so that you don't have to put your hand into this green ROI. We'd also like to accommodate for different lighting situations, and especially situations where the background might change. Here in this demonstration, the background on the ceiling is pretty static, and that's the reason why the threshold works well. Another huge area that we'd like to implement is simulating analog input. Right now, we're only able to recognize 1 through 5, and those are discrete inputs that can only send discrete commands. We might have stuff like rotating your hand or moving your hand in and out, so changing the size of the contour, to move the mouse or increase volume by some analog amount or something similar. We also might implement automatic command profile switching. So we have several YAML files which each contain different settings, and we might be able to hot switch these settings files depending on the active application.
You'd have like certain commands for like Photoshop or something, or commands for presentations. That way you can draw in Photoshop, immediately switch over to a PowerPoint, and then your controls would be completely different. All right, so for future applications, we're thinking that this could definitely be really helpful for augmented reality, which is abbreviated as AR, or virtual reality VR, essentially encapsulating kind of just natural 3D tools. So you can imagine how I could like grab an object in 3D space and kind of manipulate it around, kind of like how you see in VR systems, except you can just use your plain old hand for that instead of using a controller. And we actually looked it up, and apparently the Oculus Quest has actually just a few months ago released an update in which you're actually just able to use your hands in order to manipulate a few basic objects or use the web browser. So that would be an interesting application of what we're doing here.
What's novel about ours is that it's able to be generalized really easily using very human readable settings files and for different applications.
And second part, we're thinking smart home controls. And so you'd be able to, I guess, raise or lower the volume of something. I mean, you kind of mentioned that before, but you could like 2 fingers, open up the garage door, et cetera. Instead of using voice commands, you could just do visual commands. I know typically when I'm talking to someone and then I turn off the lights, it's kind of rude for me to interrupt them. So that would be nice. Lastly, there'd be robot manipulation. So like moving your hand left and right in order to rotate, or moving it like in and out in order to move the hand in and out. So that would be interesting as well.
We also put in a lot of effort to make this easy to use. So it's super easy to install. You just open your command prompt, type pip install OpenGesture, and then it installs the program and all of its dependencies automatically. And then you just need to type OpenGesture to run the program, as you can see on Gatlen's computer. And we also included some customization. You can type OpenGesture and specify a couple of command line arguments. -T to change the threshold depending on the lighting conditions. -C in case we have multiple cameras like Gatlen has, and also -S to customize the path to your settings file, and also -help to print out a help message.
Mhm. So you can actually download this like right after this Zoom. It doesn't actually work when Zoom is using your camera, but if you want to, you can go ahead and download this and try it out for your own. So yep, here are our citations, the original algorithms, and that's the end of our presentation. Any questions?
I had a quick question about the download. So is like everything you use for your presentation, including the debug, is that in the actual software, or did you guys just like, is it only the
We included the debug for now,
okay, yeah,
but in a future release we'd like to remove it.
all right.
We thought the debug was also just kind of cool.
Yeah, I asked.
That's cool factor points.
Gatlen, you want a Tylenol for that shoulder? You've been holding it up for a while.
Honestly, I need to get like a cast and just turn my body. Luckily, Eshan has a blank wall to like his like left or right, and so he doesn't have to put his arm up.
But yeah, hopefully, hopefully you can download this program and play around with it yourself, and maybe set up your own shortcuts to do something.
All right. Thank you guys so much for listening to our presentation. Hope you enjoyed.
Yes, thank you. Well, I feel sorry for the last group.